Hello and welcome. In this video, we're going to focus on inverse functions. We're going to talk about how to find an inverse function given a function, how to determine if the inverse of a function will also be a function, how to graph a function and its inverse, and the special characteristics that relate the two together, and lastly, to determine if two functions are inverses. So let's go ahead and jump right in. So early on in mathematics, we learned about inverse operations and how addition and subtraction are inverse operations, multiplication and division. In future courses, we learned about squaring and square rooting. We've even talked about that in this course. And all of those inverse operations, if we applied all of them at the same time, would lead us to the idea of inverse functions. Inverse operations are operations that undo each other. Inverse functions are functions that undo each other. The notation that we use for an inverse function is whatever the letter representing the function is, in this case f, and it looks like to the power of -1, but that notation means the inverse of. So this would be read f inverse of x, if we were saying out loud what that notation means. Because functions that undo each other are these inverse functions, what we're really saying is everything is switching, because we're switching the order in which we're doing things. Basically, we're changing the input and output. So if we had a point in our original function that was the point -2, -1, in our inverse function, we're flipping what those two things are. We're flipping our x and our y. So because inverse functions interchange the x and the y, we can look at their ordered pairs and flip them, and anytime we know an ordered pair in the original function, we have an ordered pair in the inverse. So any xy in the original function will be a point yx, so flipping our x and y in the inverse function. So you can see here we have a table that has a bunch of xy points that go with the function 2x plus 3. If we were looking at the inverse of x, which we're going to call g for just this example, all of those points are flipped. So all of the x's become y's, all of the y's become x's, and now we have a new table. Well, thinking about what x and y mean, what that really means is that we're also switching our domain and range. If we're switching our x's and our y's, then the domain of our original function becomes the range of our new one, and vice versa. Another unique characteristic that just comes from this idea of flipping our x and y is that means that our inverse functions have a special symmetry. They have a symmetry about the line of reflection y equals x, and that should make sense because what are we doing? We're switching y and we're switching x. So that means if we have the dotted line that you can see over here in our graph, this is the line y equals x. If I folded a function and its inverse along this line, everything would line up perfectly, because take a look at this point. This point is 1, 5 in the original function. That means this point over here, 5, 1, is the point in the inverse. And if I folded across that diagonal line, y equals x, they would line up perfectly. So the idea here is that inverse functions are switching our x's and our y's, and that creates symmetry based on the way that we're finding those coordinates. So now that we have a little bit of an idea about what an inverse function is, let's go ahead and talk about how do we find an inverse function if we're given an original function. All right, here we go. So if we're trying to find an inverse function and inverse functions undo each other, really what we're going to do is we're going to switch our x and our y. So this is written in function notation, but if I just say let y equal f of x, then I can really say this is the same thing as y equals x squared plus 2, and that, or x cubed plus 2, I'm sorry. And this is really how we think about it when we're graphing it anyways. We think about y being our output. What this means is the inverse is going to come from what happens if I flip my x and my y. So I'm just going to actually rewrite this by flipping my x and my y. So I have x equals y cubed plus 2. So the very first thing we're going to do is define y to be f of x. Then we're going to switch our x and y, and now we're going to solve for y. So to solve for y, I'm going to subtract 2 on both sides. To get rid of 2 to the third power, I'm going to take the cube root of both sides. And I'm going to make a note that could also be written to the power of 1/3. You can write that in whichever way you prefer. Then the last step, we want to get our notation right, is that we're going to write this f inverse of x as a function in function notation, because this clearly identifies the relationship between f and that this is f's inverse. So you're going to start by defining y to be f of x, flipping your x and your y, and solving for y. The one thing I didn't mention here, which I will make sure we get to in at least one of our examples, is that we need to check for domain issues. If there are x values that are not allowed to be plugged in, that's going to affect the domain of the inverse as well. In this particular function, we were looking at a cubic function. A cubic function, which looks something like this, has a domain and range of all real numbers. So does a cube root function, which we learned earlier in this chapter. So we don't have any domain issues that we need to be concerned about here. But if we have a square root function, if we have a quadratic whose inverse would be a square root function, we need to keep those things in mind. But don't worry, we'll get to examples like that. Okay. I'm going to go ahead and work through number 2 with you, and then I'm going to encourage you to try and do number 3 on your own. So the very first thing I'm going to do is I'm going to say let y equal f of x, so that I can start by flipping f, x, and y. It doesn't really make sense to talk about flipping x and y if there is no y. So x is going to equal 5y plus 7. And then I'm going to solve for y. I'm going to subtract 7 from both sides, so I'm using inverse operations here to find my inverse function. To solve for y, I'm going to divide by 5. So you could write that as x minus 7 over 5. I'm going to write it as 1/5 of x minus 7/5. This is a line, which means the domain and range are both all real numbers, so I don't have to worry about domain issues. So my final step is going to be to write it using inverse notation. F inverse of x is 1/5 of x minus 7/5. All right, go ahead and pause the video and work through number 3 on your own, and then unpause the video and see how you did. All right, so hopefully you had time to work through that, starting by defining y to be equal to f of x, writing that notation, and then identifying that we're going to find the inverse, so we're switching x and y. So the reason I'm defining y equals to f of x and making that note that we're finding the inverse is because you're really writing your math so that someone else can read it and understand it. It's like you're telling a story, and if you just immediately jump into flipping your x and your y, sometimes it's not as clear to someone looking at your work what you're doing or why you're doing it. So your goal is to make your work readable and understandable to someone else that's looking at it. So after I flip my x and my y, I'm going to solve for y. I split this into 2 fractions here. So x over 2 and 4 over 2 is 2. Then I took the cube root, which again you could write as to the power of 1/3 if you prefer. And then I rewrote my final answer using inverse notation. So none of these examples had domain issues because all 3 of these functions, their inverses, are also a function. And that actually has a special name, and there's a way for us to be able to tell if the inverse of a function is also going to be a function. So let's talk about that special type of relationship where a function and its inverse are both functions. So as I mentioned, a function and its inverse are not always, the inverse is not always also a function. So every function has an inverse, but every inverse is not also a function. Remember, a function has to pass the vertical line test, meaning I could draw a vertical line anywhere on my graph and it would only cross the function itself once. So let's look at these 2 examples here. The first one you can see in blue, the original function is f of x equals x squared, and the inverse in red is x equals y squared. The original function, x squared, passes the vertical line test, so it is in fact a function. Does the red function pass the vertical line test? Well, no. If I drew a vertical line, it would cross the function twice. So no, the inverse is not a function. That doesn't mean it doesn't exist. I see it right there. The inverse is x equals y squared, but that inverse is not a function. For the second example here, we see the original function in blue, the cubic function, and then we see the inverse, the cube root function. Now in this case, both of those functions pass the vertical line test. If I draw a vertical line, I'm only crossing each of those functions exactly one time. So g is also a function. Both f and g are functions. And there's a special name when that happens. When a function and its inverse are both functions, they are said to be invertible. Invertibility means both of them are functions. So this will make our lives a lot easier in these cases where we have a function that's invertible, or where we have a function whose inverse is also a function. We don't have to worry about domain restrictions. And that's going to make our lives a little easier. But that should also lead us to a question. Is there a way to make a function whose inverse is not a function? Is there a way to limit it so that they could both be functions? And that's what we're going to talk about next. All right, so can we use domain restrictions to help us with invertibility? So what I'm going to have you do is go ahead and graph the function f of x equals x squared. So you can do that by making a table, you can use the parent function, but just quickly graph f of x equals x squared. But while you're doing that, I want you to specifically look at only the domain from 0 to infinity. So you're only going to graph on the right-hand side. So here is that original function only looking at the positive values, and I'm just adding this dotted line which shows us where we should have that symmetry based on how we know inverses are related. They are symmetric about the line y equals x. Now if you used a table, which I'm just going to add one real quickly here, the points we looked at were 0, 0, 1, 1, and 2, 4. That's all that fit on the graph. What that means is in our inverse, we would have 0, 0, 1, 1, and 4, 2, because all we're doing is switching our x's and our y's. So go ahead and plot those 3 points. So now we have the function and its inverse, which I didn't do the greatest job connecting on this iPad, but such is life. Now, in this case, do both of these functions pass the vertical line test? And the answer here is yes. Now that we have restricted the domain, both the function and its inverse are functions, which means now we have made this quadratic invertible by modifying it to have a domain restriction. But notice that if we have a domain restriction, that everything we're plugging in here has to be positive, that is also going to restrict the domain and the range of our inverse function. So just keeping that in mind, restricting the domain in one function is going to affect the range in the other function. Now let's talk about an efficient way to tell if the inverse of a function is also going to be a function, which could help us determine whether or not we need to add a domain restriction. So we learned the vertical line test a long time ago to tell if a function is, if a graph is a function, we learned the vertical line test. Well, we can look at that same original function and use the horizontal line test to tell how the inverse is going to behave. So the horizontal line test tells us if the inverse is going to be a function. So if the inverse of f is also a function, then it will pass the horizontal line test, meaning no horizontal line crosses more than once. So here I have what looks like some sort of cubic graph. A horizontal line will only cross exactly one time, which means the inverse would also be a function. As opposed to here I have a quadratic, which we just talked about in depth. It's not going to pass the horizontal line test, which means that the inverse will not be a function because the inverse will not pass the vertical line test. So if a horizontal line only crosses a function once, then the function is invertible, or the inverse is also a function. So let's use the horizontal line test just to look at these 3 examples below and decide if their inverses will also be functions. So on number 5, if I draw a horizontal line, it doesn't really matter where I draw it. It's only going to cross once, and that means that number 5, the function 2x cubed plus 1, is going to be invertible. And I'm just going to make a little note, invertible. Or you could write that the inverse is going to be a function. So go ahead and pause the video and perform the horizontal line test on numbers 6 and 7, and then unpause the video and see how you did. All right, hopefully you had enough time to acknowledge that both of these functions are also going to be invertible. Their inverses will also be functions. They pass the vertical line test. One other thing that I want to point out is that on number 6, even though it's not written here, we do actually have a domain restriction. It's not explicitly stated, but what we learned earlier in this chapter is that the domain for this function inside a square root has to be positive. So the domain has to be greater than or equal to 3 for our original function, and that is going to affect the domain and the range for our new function as well. So we'll talk about that a little bit more when we start graphing. Okay, let's go ahead and find the inverse, and then we're going to talk about graphing, and I'm actually going to just use the ordered pairs that are there to graph the inverses. So to find the inverse, I'm going to let y equal 2x cubed plus 3, and then I'm going to look at the inverse. So I'm going to switch my x and my y. X equals 2y cubed plus 1, and then I'm going to solve for x. So x minus 1 over 2 equals y cubed. So y is going to be x minus 2 over 1 to the 1/3 power, or the cube root of that, whichever you prefer. Now I'm going to write it as a function, so f inverse of x is going to be, and I'll write it as a cube root so you can see it both ways. Now I don't have a great shortcut for graphing this particular function. I could use transformations, but since the original function is already there and I know that inverses just switch the x and the y, I'm going to just go ahead and identify a few points that I can see and that I know are on my original function. So I see the point 0, 1, I can see the point -1, -1, I can see the point +1, 3, and I could also check that those are actually on my graph here. What that means is in my inverse, I'm going to have the point 1, 0, -1, -1, and 3, 1, and then I can go ahead and graph those 3 points. I'm going to add in that line of reflection because it helps me when I'm trying to figure out the shape here, right? Because it should be that I can fold this and everything lines up. So here I have, to the best of my ability, I could probably do a little better, a sketch of that function's inverse. And I can see from this graph that it is invertible, which verifies what I originally thought. So go ahead and pause the video, and for 6 and 7, solve so that you have the inverse written as a function, and then maybe try and identify a few points on each of the graphs that you could use. So I'm just going to kind of mark off what I'm seeing that you could use to write your inverse function. Then unpause the video and see how you did. So here I have my inverse function for number 6. And what I notice is that originally the domain was that x had to be greater than or equal to 3, and the range for f was that there's no vertical translation here, so that the range was that we had to be greater than or equal to 0. So the domain of my new function is going to be what the range of my original was. The domain of my inverse is going to be what the range of my original function was, which I'm going to see when I plot these points as well. So here I listed out the points, and now I flipped my x and y to list out the reciprocals, or not the reciprocals, but the inverse points. So 0, 3, 2, 4, 4, 7, and you can add in that dotted line if it helps you with the shape y equals x. And there is my sketch. So I'm going to encourage you to do number 7 on your own if you haven't already, and then unpause the video and see how you did. So here we go. I started by defining y to be f of x, and then since I'm finding the inverse, switching my x and my y and solving for y. Now I distributed the 1/3, but you could have left everything over 3 or left the 1/3 in front like it is here in this step. Now I could either plug x values in here, or I can identify these 3 points and switch the x and y values to get that shape. So I'm going to go ahead and identify those 3 points. I'm going to add my dotted line y equals x where I have my symmetry, and then plot those points. So I have connected those points to the best of my ability, and it looks like if I folded it across this dotted line y equals x that everything would line up. All right, let's move into our very last topic, which is determining if two functions are in fact inverses. Okay, so this last circumstance, we're going to be given two functions and we're going to be asked if they are inverses. So we're going to determine if each function is the inverse of the other function. So what we're going to do is, since we know that inverse functions switch our x and our y value, what that really means is if we plug one function into the other, so if we let y equal f of x in the same way we have been doing, and simplify, everything should simplify away to give us just x. So if we plug, and I know this notation might look different, if we plug g of x into f of x and simplify everything away and get x, and by contrast, if we plug f of x into g of x and simplify and get x, then we have two functions that are inverses. So I know that notation can be a little confusing, but really all we're doing is we're saying, I'm going to take one function, I'm going to substitute this in for the x in the other function. So f of x, instead of it being 3 times x minus 1, where there was an x, I'm going to plug in g. Then I'm going to simplify. So if I have this 3 on the outside and this 3 in this fraction, that 3 in the denominator and the 3 in the numerator are going to divide out. So this is going to simplify to be just x plus 1, and then this minus 1 out here, and that's going to simplify to just be x. So far, so good, because what this means is that this shouldn't say f of x, this should say f of g of x is equal to x. Now we're going to see what happens if we plug f into the g function. So g of f of x. So g of x says x plus 1 over 3. But where there is an x, we're going to plug in f, which is 3x minus 1. And again, we're going to simplify. So let's simplify the numerator. This says 3x minus 1 plus 1. So the 1's are going to add to be 0. And then the 3's are going to divide to be 1, so we just have x. So in this case, f and g are inverses. So the expectation that I have for you is that you are testing both f of g of x, as it says in step 1, and g of f of x, as it says in step 2. So let's look at number 9 together, and then I'll have you try number 10 on your own. If I want to verify or check whether or not these are inverses, I need to take g of x and substitute that into x in my f function. So f of g of x, so what I get in f when I plug g of x in for x, so g of x is x minus 5, and f of x is whatever we're plugging in plus 5. And then we're going to simplify. Well, x minus 5 plus 5 is just x. So far, so good. Now I'm going to do the reverse of that. I'm going to take g of x, which is x minus 5, except everywhere there is an x, I'm going to replace f of x, x plus 5. So again, I have x plus 5 minus 5. This is going to equal x. That means that f and g are inverses. So go ahead and pause the video and work through number 10 on your own, and then unpause the video and see how you did. All right, so what I did here, I didn't simplify all the way because I wanted to walk through that with you in case you were getting stuck. But f of g of x, I took g of x and I plugged it in for x. So here in green is g of x, and everything in purple is f of g of x. And then down here, g is the green function, and I'm plugging in the purple function here for x. So now I need to simplify to check and see, does it simplify to just be x? So here, if I square a square root, I just am left with what's on the inside. So I'm going to have 5 times x plus 2 over 5 minus 2. These 5's are going to divide out, which leaves me with x plus 2 minus 2, which is going to be x, which is what I'm looking for. For g of f of x, I'm going to simplify inside the square root. So the plus 2 and the minus 2 are going to be 0. So I have 5x squared over 5. The 5's can divide out. The square root of x squared is just x, and that's what I'm looking for again. So g and f are inverses. So in order to check, you're going to plug one into the other and simplify. If you get x, then you're going to check the other one. If you don't get x, then they're not inverses. There's no point in checking the other one because it has to be true for both. So let's recap what we covered in this video. First, we defined what an inverse is, and we talked about how an inverse is a function that undoes a function. We talked about the notation where we have that f, what looks like f to the power of -1 of x. That's how we define f inverse. We talked about how to find the inverse given a function, an appropriate notation for that. Then we talked about whether or not a function is invertible, whether or not the inverse of a function is also an inverse, and how we can possibly adjust the domain or deal with domain restrictions to help us with that. We talked about the horizontal line test and sketching functions and their inverses. And lastly, we talked about determining if two functions are inverses of each other. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.